Hi everyone, Kate Lynch here. So this is my basic concepts or advanced concepts presentation 5. So we're going to be talking about the generation of ATP through cellular respiration, all of the, formulas for how it's formed and generated and ultimately develops 30 ATP per 1 molecule of glucose. And there we go. Okay, so basically a lot of stuff is going on at once. So we have glucose that's happening and it's changing into pyruvate, or glycolysis that's happening and has glucose changing to pyruvate and then ends up going to the citric acid cycle and that's producing ATP. We have the electron transport chain carrying stuff on over to oxidative phosphorylation, creating more ATP. So there's a lot of stuff going on, a little overwhelming, but we're going to break it up and then at the end I'll show you how everything comes together. Okay, so first we'll start with glycolysis. So one molecule of glucose is broken apart and it forms 2 pyruvates. So on a net basis, 2 new ATPs are generated during glycolysis. 2 are used, 4 are actually generated, so if you cancel those out, 2 are ultimately formed. So during glycolysis, 2 NAD molecules are also reduced, or they gain an electron and they form NADH, and then that actually plays a role into oxidative phosphorylation, which I'll talk about later, and that produces even more ATP. So now if oxygen is present, we'll continue to the pyruvate dehydrogenase complex, and then that will form acetyl-CoA, during which 2 NADHs will be produced from the conversion of the pyruvate to acetyl-CoA. So ultimately, we have glycolysis here. We have 2 ATPs formed, 2 NADHs formed, and then we also have the pyruvate dehydrogenase complex, and it's important to know that there are 2 NADHs that form out of that. Okay, so now we're going to go into the citric acid cycle. As we know, glycolysis and the citric acid cycle are linked together by the pyruvate dehydrogenase complex, so that's important. We just went through that. So now we're thinking about the CoA that was just formed from the pyruvate dehydrogenase complex. So that acetyl-CoA that is produced will actually act as the fuel for the citric acid cycle. Throughout the cycle, we'll go to each intermediate in the cycle and continue to reduce NAD to NADH, and this actually happens 3 times. Until we reach oxaloacetic acid for each pyruvate. So this actually happens twice because 2 pyruvates are formed during glycolysis initially. So at this point, we can accept the CoA again from the pyruvate dehydrogenase complex, hence this makes this a continuous cycle, so it's just going around and around in a nice circle. CO2 is also released as well as ADP is being converted to ATP, and FAD is also reduced to FADH, and this also happens twice. So these are really key things that we need to recognize before we reach oxidative phosphorylation, which I'll talk about in a second. So key things to know: citric acid cycle, we end up with 2 ATPs and we have 6 NADHs and then 2 FADHs. So this is all super important. We have to remember that everything is happening twice because of the 2 pyruvates, and that's how we get each number. Okay. So now we have oxidative phosphorylation, and this part is really important because this is what makes the majority of that 30 ATP from the 1 glucose molecule. So we have NADH, and it's actually oxidized to NAD plus H plus 2 electrons. So NADH ends up being the driving force for making ATP and oxidative phosphorylation. So we have 2 electrons plus 2 hydrogens plus 1/2 of oxygen, and this equals water. But if this reaction happens super fast, as you can see right here, it'll release so much energy that we won't even be able to use it or absorb it. So this reaction actually takes place in steps from 1 electron acceptor to the next and to the next and so on, while it releases a little bit of energy little by little. So this is actually the electron transport chain. The electron will go to coenzyme Q and then cytochrome C, and then it will travel until the oxygen can accept it, all while releasing energy. So the shuttle allows 2 molecules of NADH to yield 1.5 molecules of ATP, ultimately 3. So then, all in all, everything is happening. Oxidative phosphorylation actually ends up creating 26 ATPs, so there's a lot. So I have a chart that's coming up that'll really show how everything's going on. So it's kind of a summary, so I'll just backtrack a little bit. So we're back into glycolysis, and I said that it uses 2 ATPs, and then it actually creates 4, so technically it only creates 2, because that's what we have left. So we can see that over here, -1, -1, so those are the 2 that we're using. And then we're making 2 more, and then 2 more again. So ultimately, there's 4, but there's actually 2. And then we have the conversion of pyruvate to acetyl-CoA, or the pyruvate dehydrogenase complex. And that's when there's the 2 NADHs that are formed that I explained earlier. They come into play over down here in oxidative phosphorylation. And then we go to the citric acid cycle, and as I said before, we are developing 2 molecules of ATP, and then we're actually also getting 6 molecules of NADH and 2 FADHs, which are really important for oxidative phosphorylation eventually as well. So just some key things, but we also just have 2 little ATPs. And then we're getting down into oxidative phosphorylation, and now we're inside the mitochondria, of course. Everything, glycolysis was in the cytoplasm, everything else is inside. And so we have 2 molecules of NADH, and they're finally being used, and they actually yield 1.5 molecules of ATP, and then that's times 2, so 3. And then we have 2 molecules of NADH again. That's formed from the oxidative decarboxylation of pyruvate, which happened up here, pyruvate dehydrogenase complex. So that's that little leftovers, and it is used and forms 2.5 molecules of ATP. This is twice, so 5. And then we have 2 molecules of FADH, which was formed in the citric acid cycle, as I said before. Each yield 1.5 of ATP. This is twice, so 3. And then finally, we have those 6 molecules of NADH that the citric acid cycle formed. And that was the really important one. That's where the most ATP is actually going to come from. Each one yields 2.5 molecules of ATP, and that creates 15. And then that is how we get the 30 ATP molecules, or ATPs per 1 glucose molecule. And that is all. Thanks.